In this video, we will see some numerical methods for the solution of system of linear equations. So we have to study system of linear equations. Now for the methods of solution of system of linear equations. In case of numerical methods, we have two type of methods. One is direct methods, another one is indirect methods. So here, the numerical methods for the solution of linear equations can be categorized into two types of methods. One is direct methods and another one is indirect methods. Sometimes the direct methods are also called as elimination methods. Elimination methods, because these involve elimination approach in the method used. So they use elimination approach, and the indirect methods are sometimes called as iterative methods. And because they use iterative approach for the methods involved. Now basically the methods of the solution of system of linear equations are categorized into direct methods as well as indirect methods. These direct methods involve elimination approach and indirect methods involve iterative approach. Now we will see different direct methods one by one. The first direct method is Gauss elimination method. So, and the second is Gauss-Jordan method. Third one is matrix inversion method. Fourth one is LU decomposition method, and the fifth one is Cholesky factorization method or Cholesky decomposition method. Now coming to Gauss elimination method, again this because it is involving elimination, therefore elimination approach are here used. Gauss elimination is nothing but elimination of, here the given problem is in terms of Ax is equal to B, which is a system of linear equations. Here A is a square matrix, X and B are column matrices or column vectors. Now Gauss elimination is again categorized into Gauss elimination without pivoting, Gauss elimination with pivoting. Here basically in the case of Gauss elimination method, we are converting Ax into B as some upper triangular matrix, some U dash X is equal to some B dash or sometimes L dash X is equal to B dash. So our aim is to convert the given matrix A into either upper triangular matrix or lower triangular matrix, upper or lower triangular matrix. After the elimination approach, the final matrix will be in terms either upper or lower triangular matrices. So in converting the matrix into either upper triangular or lower triangular matrix, we are performing some operations. So the operations are row operations. Usually row operations are performed in case of Gauss elimination method. So here we have one term that is without pivoting. Without pivoting means we are not supposed to exchange any row or column. So any row or column before the procedure. So here in case of with pivoting, we have to exchange rows or maybe sometimes columns. Exchange rows or columns. Exchange rows or columns, sometimes both. So therefore they are called as with pivoting. Here in case of with pivoting also we have two categories. One is partial pivoting and one is complete pivoting. Partial pivoting means only exchanging of rows is possible. Exchanging of rows is considered. Here both rows and columns can be exchanged. So this is about partial pivoting and complete pivoting. Whatever the method may be, the Gauss elimination involves the process of row operations so that the matrix after the Gauss elimination process will be either upper triangular matrix or lower triangular matrix. So this may be U dash X is equal to B or sometimes L dash X is equal to B dash. So with the help of U dash and L dash, either with the help of back substitution or forward substitution, X values can be found out. So this is about Gauss elimination method. We have to remember, in the case of Gauss elimination method, we have to perform row operations so that the given matrix A is converted into either upper triangular matrix or lower triangular matrix, and with the help of backward substitution or forward substitution, the X values are obtained. Here in the case of Gauss elimination method, we have again categorized into with pivoting and as well as without pivoting. Without pivoting means it doesn't involve any exchange of rows or columns before the procedure is started. In case of with pivoting, we have to exchange either only rows or we can exchange both rows and columns. If you exchange only rows or only column, that is called partial pivoting. If we exchange both rows as well as columns, that is called complete pivoting. What we have to remember is that after the Gauss elimination process, we will be arrive at the either upper or lower triangular matrix. This has to be remembered. Upper or lower triangular matrix. This has to be remembered about Gauss elimination method. Now coming to Gauss-Jordan method, here the system of equations is in terms of x is equal to b. We have to perform both row and column operations, so that we have dx is equal to b dash. After the operations, here we have to perform both row and column operations for system of equations x is equal to b, so that we will be arriving at the system that is dx is equal to b. Here d is a diagonal matrix. With the help of diagonal entries. So if you have d1 x1 for the first entry, this is equal to b1, then x1 will be obtained with the help of b1 by this is d1. So this is how the x values are found. What we have to remember about Gauss-Jordan method is that after the row and column operations, we will be arriving at the diagonal matrix. This has to be remembered. Diagonal matrix is obtained here at the end of Gauss-Jordan process. Now matrix inversion method. Here Ax is equal to b is a system of equations. If suppose A is invertible, determinant of A is not equal to 0, then x will be obtained in terms of A inverse of b, A inverse into b. So this is how the x values are found out with the help of inverse of a matrix. So just you have to remember the formula for matrix inversion method. Now next method is LU decomposition method. Here again we have system of equations x is equal to b. We have to write A as A is equal to L into U. Again, based on the entries of L and U, we have two different methods. One is Doolittle method, another one is Crowd's method. If suppose L is like L11, 0, so on, L12, L21, L22, so on, Ln1, Ln2, so on. This is Ln. If suppose all the diagonal entries for this lower triangular matrix is 1 or Lij's are 1, Lii's are 1, then this is called Doolittle method. If in case of for the upper triangular matrix U11, so that UNN, this is U1n, so on. These are 0, these are zeros. If suppose all UII's are 1s, this is called Crowd's method. So what we have to remember is that in the case of LU decomposition method, the square matrix A is factorized into L and U. Based on the entries of L and U, we have some two different methods. In case of Doolittle method, if suppose all the diagonal entries of Li's are 1 and UI's are same as U12, U13 like that, and in case of Crowd's method, all the diagonal entries of UI's are 1s. So this is about Crowd's method. So we can rewrite this as just rewrite them as, in the case of Doolittle method, diagonal entries of L is equal to 1. Here in the case of this, diagonal entries of U is 1. So this is about LU decomposition method. Next one is Cholesky factorization method. Here we have x is equal to b, a system of linear equations. Here if A is symmetric and positive definite, then A can be written as A is equal to L into L transpose, where L is a lower triangular matrix. For system of equations x is equal to b, if suppose A is symmetric and positive definite, then A is equal to L into L transpose is a Cholesky decomposition of A. Or if A is a complex matrix, here in case of real matrix, if it is a complex matrix, then if A is Hermitian and positive definite, then A is written as A is equal to L into L transpose. Then such decomposition is called Cholesky decomposition. So here in case of Cholesky decomposition, Here A should be symmetric and positive definite in case of real matrix, and it should be Hermitian and positive definite in case of complex matrix. If that follows, then that A can be written as L into L transpose. Then such a decomposition is called Cholesky decomposition, or sometimes it is called Cholesky factorization, or sometimes it is called as Cholesky. So sorry. This is Cholesky factorization or Cholesky decomposition method, or sometimes it is called as square root method. So this is about Cholesky decomposition method. One thing we have to remember is, so what is symmetric matrix? Symmetric matrix is that A transpose is equal to A, and that is symmetric matrix. If it is Hermitian means A theta is equal to A. A theta means transposed conjugate of A. This is about symmetric and Hermitian matrices. One term we have positive definite. What is positive definite then? Positive definite matrix means if all the eigenvalues of A are greater than 0, or sometimes we can write it as if all the leading principal minors are greater than 0. All the leading principal minors are greater than 0, then those are called as positive definite matrix. In case of eigenvalues, if all the eigenvalues are greater than 0, then those are called positive definite matrix. If it in case of all the leading principal minors, if all the leading principal minors are greater than 0, then those matrices are called as positive definite matrix. One thing we have to remember that these methods, Gauss elimination method, Gauss Jordan method, matrix inversion method, LU decomposition method, and all the methods will be, they will give the solution or they will converge only when A is diagonally dominant. So these methods, Gauss elimination, Gauss Jordan, and LU decomposition, they will converge when, or sometimes we can use this for here we are having positive definiteness. Here in case of Gauss elimination and Gauss Jordan methods, they will have a exact solution only when A is diagonally dominant matrix. Oh, what is diagonally dominant matrix then? Diagonally dominant matrix will suppose A11, A12, so on A1n, A21, A22, dash AN1, AN2, so on AN. It is a square matrix of order n. If suppose these diagonal entries AI is modulus of diagonal entries, if they are greater than or equal to, sometimes greater than all the entries in the particular row, this is nothing but AI1 plus AI2, so on AIN. Suppose I is equal to 1, A11 is greater than A11, no, that is A12, A13, so on A1n. If these diagonal entries, modulus of the diagonal entries are greater than the sum of the modulus of different other entries. For example, we take, suppose we have matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. If suppose modulus of A11 is greater than modulus of A12 plus modulus of A13, and modulus of A22 is greater than modulus of A21 plus modulus of A23, and modulus of A33 is greater than modulus of A31 plus modulus of A32, then this matrix is of order 3 is called diagonally dominant. So what we have to remember is that this Gauss elimination method and Gauss Jordan method, they will converge when the matrix A is diagonally dominant. And one thing we have to remember is that the matrix X in X is equal to B, A is Cholesky decomposable. Case 1 is for A is real matrix, and case 2 is A is complex matrix. This is Cholesky decomposition if A is symmetric in case of real and positive definite, and in case of complex matrix A is Hermitian and positive definite. Then here symmetric means A transpose is equal to A. Here in case of Hermitian it is A theta is equal to A. A transpose is nothing but transpose of A theta is nothing but transposed conjugate of A. Here for both positiveness means all the eigenvalues are all eigenvalues are greater than 0, or in case of principal minors, or all the leading principal minors are greater than 0. For example, we take, if suppose a11, a12, a13, a21, a22, a23, a31, a32, a33. If suppose modulus of the determinant of a1 is greater than 0, determinant of a11, a12, a21, a22 is greater than 0, and a11, a12, a13, a21, a22, a23, a31, a32, a33. This modulus determinant is greater than 0, then this is positive definite, or it has all positive eigenvalues, positive definite. Therefore, we have to remember that. So here, for the Cholesky decomposition to happen, whether in case of real matrix A is symmetric and positive definite, or in case of complex matrix it is Hermitian and positive definite. In that case only the decomposition is possible, that is given by A is equal to L transpose. A is equal to L into L transpose. This is the Cholesky decomposition of A. It is possible only when it is a symmetric or Hermitian in case of different entries, and it should be positive definite. This should be remember about Cholesky decomposition. And one thing also we have to remember about Cholesky is this Cholesky decomposition if it exists only for the matrices which follow these two rules. If it exists, then it will be unique. So this is about the Cholesky decomposition method. Now we have seen this Gauss-Jordan and Gauss elimination. We have to remember, what we have to remember is that this Gauss elimination and Gauss-Jordan methods, they will converge or give the root. Converge when A matrix A in is diagonally dominant. So that the things should be remembered about the Gauss elimination, Gauss-Jordan. So in case of Gauss elimination, after the elimination approach, we have either upper triangular or lower triangular matrix. In case of Gauss-Jordan method, we have the matrices after the elimination approach, we have diagonal matrix. Here we can follow either backward substitution or forward substitution in order to get the root. Backward or forward substitution to get the roots. Here directly obtained with the help of diagonal entries. So in case of Gauss elimination, we are exchanging either rows or columns in order to make them as diagonally dominant. Sometimes what happens is, this will be 0, this is 5, this is 1, this is 2, this is 8, this is 1, and this is 2, 3, this is 9. So here you can observe A11 is 0 and A22 is 8 and this is 9. No, this is 12. Then we can exchange row 1 and 2, so that it will become 12, 8, 1, this is 0, 5, 1, 2, 3, 9. Just now we can observe, so 12 is greater than modulus of 8 plus 1, that is 9. 12 is greater than 9, here it is 5 is greater than 1, here 9 is greater than 5. So now it becomes diagonal dominant. Sometimes in order to make the given matrix as diagonal dominant, we have to exchange with the rows or columns. Then therefore we will be having a concept of pivoting. So the concept of pivoting is introduced in order to make the given matrix into diagonally dominant matrix. Therefore the methods Gauss elimination and Gauss-Jordan will converge only when the matrix is diagonally dominant. And Cholesky decomposition is possible only when the matrix is symmetric and positive definite in case of real matrix, and that is Hermitian and positive definite in case of complex matrix. If the Cholesky decomposition exists, then that will be unique. These are the things to be remembered about Cholesky decomposition and Gauss-Jordan and Gauss elimination methods. Now we will be seeing one more method, that is called as LU decomposition method. We will see some things about some important facts about LU decomposition method. These are, not all the square matrices have LU decomposition. So suppose Ax is equal to B, then A need not be having, it may or may not have LU decomposition. So therefore we have to remember not all the square matrices have LU decomposition. So not all the square matrices have LU decomposition, this should be remembered. If a matrix has LU decomposition, if a matrix has, suppose there is a LU decomposition, if suppose X is equal to B, the system of equations, if suppose A is equal to LU is a LU decomposition of A, then it need not be unique. It may exist or may not exist. If it exists, it may not be unique. It has to be remembered. Now the third option is, the third important point says LU decomposition is possible for all positive definite matrix. X is equal to B, system of equations. A is, if suppose A is positive definite, then LU decomposition will exist. It may or may not be unique. May or may not be unique. You don't think about that. May or may not be unique. So what we have to remember is, not all the square matrices have LU decomposition. If a matrix has LU decomposition, then it may not be unique. If suppose the matrix is positive definite, then it has LU decomposition. Then also it may or may not be unique. And the fourth point says, if a matrix is invertible, non-single means invertible. If a matrix is invertible, then LU decomposition is unique. Suppose there is invertible matrix. Suppose A is invertible matrix. In the case of X is equal to B, is invertible, and if it has LU decomposition, then this is unique. So it should be invertible, and if it has LU decomposition, then it will be unique. Next one is, every diagonally dominant matrix is LU decomposition. Every diagonally dominant matrix is LU decomposable. If suppose X is equal to B is a system of linear equations, A is diagonally dominant, then it should have LU decomposition. So if it is diagonally dominant, then it will be having LU decomposition, but we don't know whether it is unique or not. But if it is invertible, then we say that it is unique. Therefore every diagonally dominant matrix has LU decomposition. We have to remember that. Now in case of invertible matrix, if A is a invertible matrix, then A has LU factorization if and only if. If A is invertible and it is LU factorizable, can we consider matrix A is invertible, then A has LU factorization if and only if all the leading principal minors are non-zero. Suppose we have a matrix A which is invertible, then this has LU factorization if and only if all the leading principal minors are greater than 0. That means LU factorization, if A is invertible matrix, then LU factorization implies all the principal minors are non-zero. If A is invertible and all the principal minors are greater than 0, then it will be LU factorization. This is if and only if, both the ways it is possible. These are some important things about LU factorization method. This has to be remembered because some questions were asked based on these parallel statements only. Now we will see indirect methods. So indirect methods are sometimes called as iterative methods because they will involve iterative approach for the methods involved. The first one is Jacobi's method, and the second method is Gauss-Seidel method. We will see the methods one by one. First method is, those are iterative methods. The first one will be Gauss iteration method, called iterative method, Gauss iteration method, and the second one is Gauss-Seidel method. Gauss-Seidel method. Here again we have the sum of equations X is equal to B. In case of both, here we can decompose A into L plus U plus T. Here L is strictly lower triangular, this is strictly upper triangular, and D is triangular matrix. Here also A is split as L plus U plus D. So therefore we can write it as L plus D plus U into X is equal to into X is equal to B. Here also L plus D plus U into x is equal to B. So for the case of Jacobi iterative method, we can group dx one side and L plus U one side is equal to B. Therefore dx is equal to minus L plus U x plus B. X is equal to minus D inverse of L plus U x plus D inverse B. So therefore x becomes minus of D inverse L plus U. Therefore we can write it as, if suppose the iteration is k plus 1th iteration, then the relation between k plus 1th and kth is written as x power k plus 1 is equal to minus D inverse of L plus U x raised to k plus D inverse B. So this is a formula for Jacobi iterative method, which involves the relation between k plus 1th iteration value and kth iteration value. Here x raised to k plus 1 is values of x in kth iteration, in k plus 1th iteration. Yeah, that is, other one is the kth iteration. So this is the formula for Jacobi iterative method. Similarly, in the case of Gauss-Seidel method, we can group differently. That is d plus Lx plus ux is equal to b. You can write it as d plus Lx is equal to b minus ux. So therefore x is equal to minus, you can write separately. This is Gauss-Seidel. X is equal to b. Here we have written a as d plus L plus u x is equal to b. We can group d plus L one side and u one side is equal to b. So d plus L x is equal to minus ux plus b. X is equal to d plus L inverse ux is plus d plus L inverse b. So this is a formula for Gauss-Seidel method. For the k plus 1th iteration, we have x power k plus 1 is equal to minus d plus L inverse into u into x power k plus d plus L inverse into b. This is the general formula for Gauss-Seidel method, which involves k plus 1th iteration and kth iteration. We have to remember this. And one more thing we have to remember, that some important points are: first one, Jacobi iterative method. Jacobi iterative method is sometimes called as method of simultaneous displacement. And second point is, Gauss-Seidel method is called successive displacement method. Successive displacement method or method of successive displacement. This have to remember. And one more thing about the convergence: both Jacobi and Gauss-Seidel method will converge to the root. Only when A is strictly diagonally dominant. So both Jacobi as well as Gauss-Seidel methods will converge only when the matrix A, in case of x is equal to b, is strictly diagonally dominant. There is slight difference between diagonally dominant and strictly dominant. That is diagonally dominant versus strictly diagonally dominant. So that is nothing but, suppose A is a matrix of order 3, then if suppose modulus of a11 is greater than or is equal to a12 plus a13, a22 is greater than or is equal to a21 plus a23, a33 is greater than or is equal to modulus of a31 plus modulus of a32. So then this is diagonal dominant. If suppose a11 is strictly greater than a12 plus a13, a22 is greater than a21 plus a23, a33 is greater than a31 plus a32. This is strictly diagonal. So we have to remember Gauss-Jordan and Jacobi iterative and Gauss-Seidel. These will converge only when A is strictly diagonal dominant. This is strictly diagonal, should be noted. And in case of, we have seen, so this Gauss elimination and Gauss-Jordan will converge when they are diagonal dominant. Just diagonal dominance is needed here in case of direct methods, and in case of these iterative methods they should be strictly diagonal dominant. These are some important points about the methods of solution of system of linear equations.